Hi everyone, and welcome to lecture 31 on the net change theorem. So in this lecture, we're going to first talk about what indefinite integrals are, and then I'm going to talk about what the net change theorem is, and we'll cover a few applications using the net change theorem. So, indefinite integrals, when I write something like f of x dx, this is used to describe a family of antiderivatives of f of x. So remember, you can have many different antiderivatives of a function as long as the derivative of what you find is the original function, then it qualifies as an antiderivative. So we say that the integral of f of x dx is the indefinite integral. And the distinction you just need to know is if I don't give you bounds for this, if I don't tell you where we start and where we're going, that's just called indefinite. I haven't given you actual bounds for the integral. So let's take a look at this example. So to integrate x squared dx, I have to find the antiderivative. So this is going to be x cubed if I increase the power by 1 and then divide by the new power. But for this, because I haven't specified the bounds, we could have any constant we want here. And then if I took the derivative of this, I would get back to x squared. So this is what I mean by a family of antiderivatives, because, oh, I spelled derivatives wrong over here. I just noticed that. Antiderivatives. OK, anyway, sorry, that would have bugged me. So taking the derivative of this with any constant here gets us back to the original. So really, you could have any constancy you wanted. And this is the answer to the indefinite integral problem over here. OK, let's do another one. So here, no bounds. So I know that this is an indefinite integral. This might be hard to integrate as is, but what I'm going to do first is just distribute this x in here to make this look better. So this is x times 1 is x. And then I get plus 2x to the 5th dx. And now I can take care of this just like the other one. I just have two separate integrals here. I have the integral of x dx plus the integral of 2x to the 5th dx. This one, if I increase the power by 1, I get x squared, divide by the new power, plus, for this one, I increase the power to a 6, and then the new power goes down here, but I also had a 2 that was just kind of floating in front. And then to complete this indefinite integral, I need to put plus c, because I could have had any constant. So it doesn't matter that I have two separate integrals. Together, they will contribute some constant here when I find the antiderivative. So this would be the answer to my general the general indefinite integral problem. OK, so here's this one. I guess I could have simplified, huh? I could have did 1 and 3 here. Here's another one. So this one is called a definite integral, and we've encountered that in a previous lecture. So this is a definite integral because I'm telling you my lower bound is 0 and my upper bound is pi over 4. So we're actually going to get to plug in these numbers once I've found the antiderivative, and I won't have this plus c anymore. So this is called a definite integral. Let's get to work on it. So this is 0 to pi over 4. I have a single term in the denominator, so I can divide that into each of them. 1 over cosine squared. What trig function would that be? This is going to be secant squared theta, because 1 over cosine is secant. Here I have cosine squared over cosine squared. Anything over itself will just be 1. d theta. D theta just means we're considering theta to be the independent variable this time. So these two match up, so this is just theta is our variable. Now I need to integrate this. What function has secant squared as its derivative? So we're thinking backwards. It should be tangent, right? Tangent theta would have secant squared as its derivative. And how about 1? Well, it's not x this time. It's theta. So this would be theta to the first power. And then if I did take the derivative of this, I would get back to here. I don't include a plus c this time because I have bounds to plug in. I have pi over 4, and I have 0. tangent at pi over 4 is 1. And then if I plug in pi over 4 for theta, I just get pi over 4 minus tangent of 0 is 0. And then if I plug in 0 here, I just get 0. So the answer to this is just 1 plus pi over 4. Some unit circle stuff coming into play there. OK, so I've explained the difference now between an indefinite integral and a definite integral. Moving along, we're going to talk about the net change theorem, and I'm going to give you a few applications to velocity and position and total distance traveled. So I'll see you in just a second. So now we're going to use let's now take a look at the net change theorem. So here's how we start this. So we're going to apply the fundamental theorem of calculus, part 2 from our previous lecture. So this is fundamental theorem calculus part 2. And then we get the following theorem. So the integral of a rate of change is the net change. And the way I express that using math symbols here, let me try changing my color and seeing if this works a little better. This would be the integral from a to b of a rate of change. So say I have a function f of x. The derivative gives the rate of change of f of x. So the integral of a rate of change is the original function evaluated at the end of the interval minus the function evaluated at the beginning of the interval. And if you go back to your notes on what the fundamental theorem of calculus part 2 says, it's exactly this. So to evaluate some function here, all you need to do is find the antiderivative and then plug in the two endpoints. So that is the fundamental theorem of calculus part 2. So here's an example that we can apply this to. So if an object moves along a straight line with position function s of t, so that's s of t, then its velocity is v of t equal to the derivative of s of t. So this is review of our rates of change lecture. However, now, by the net change theorem, we have the following. So the integral from the beginning of the interval time 1 to the end of the interval time 2 of the rate of change. So this time, velocity is the rate of change. That's how we measure the change in position. So this is the rate of change. It's equal to the position at the end of the interval minus the position at the start of the interval. So here our f prime is v of t. And we know to integrate velocity would give us the position. So it's equal to the position function at the two endpoints, so the difference between them. However, we know this as something else. What is the final position minus the initial position called? That's called displacement, right? So this is the displacement from t1 to t2. So this is just another way of describing the displacement. So here's an example. A particle has velocity given by, and I'll give you the formula for this one, v of t equals t squared minus t minus 6. And this is measured in meters per second. It's a velocity. So this is the velocity function for a particle. And we're going to find the displacement from t equals 1 to t equals 4. So let's use what we just went over here to solve this problem. So what I'm going to do is I'm going to find the displacement using this formula. So my displacement, or the change in position, is equal to the integral of the velocity function. And this is going to be from 1 to 4, because that's what the problem specifies. And now I can go ahead and plug in what my velocity is. So the velocity function is t squared minus t minus 6. And then if I go ahead and integrate that, I use the power rule 3 times backwards. So this is going to be t cubed over 3 minus t squared over 2 minus 6t. And I need to evaluate that from 4 to 1, because this is a definite integral. So first you plug in 4 into this, and you get 64 over 3 minus 16 over 2 minus 24. And then here you have to be careful. So you minus, and you're going to put a giant bracket, and you're going to plug in 1 now. And that result's going to go in the brackets. So this is 1/3 minus 1/2 minus 6, close brackets. I will save you the trouble here. So I calculated this 6-term thing, and I ended up getting negative 4.5 meters. So it's in meters because what we found was a change in position. And it's negative because from where it started, it went to the left by the time it was done. When this whole time interval was over, it ended up 4.5 meters to the left of where it started. Let's look at another application now using the net change theorem. So here's another example. So if we want to find the total distance traveled, we need to consider intervals where the velocity is positive and intervals where the velocity is negative. So we saw this when we were calculating total distance traveled. You want to separate the intervals into only intervals where you're going just to the right and just to the left, and then you add them up separately so you don't accidentally undo some of the distance that the particle or whatever it is traveled. So for this, we have a formula then. The total distance traveled, this is given by the integral from t1 to t2. So same beginning as that, but you're going to take the integral of the absolute value of the velocity function. So we're going to keep this in here positive, and this will keep track of the total distance we traveled. So let's take a look at an example of this. So we're going to find the total distance traveled for the previous example. So this one right over here. So what I need to do to set up this a little differently is I'm going to say the total distance, well, this is equal to the integral from 1 to 4, because that's the interval we used before, of the absolute value of the velocity function, dt. Well, this is equal to the integral from 1 to 4. Let me plug in my velocity function. It's t squared minus t minus 6 dt. And then this is equal to the integral from 1 to 4, the absolute value of t minus 3t, and then t plus 2 dt. So in this step, all I've done is I've taken this quadratic and I've factored it out. OK, so I need to deal with this absolute value right now because we can't really take the integral right now. So let's do some scratch work over here. I'm examining t minus 3, t plus 2, and I'm going to mark off my number line here with minus 2 and 3. These are the points where the particle switches from moving right to left, because that's the zeros of this. So I need to figure out where this is positive and where this is negative. So if I test, let's say 0 here, and 4 here, and we'll test negative 4 here. If you plug in 0 into the velocity here, you're going to get a negative. And if you plug in negative 4 here, the velocity will be a negative times a negative is a positive. And if you were to plug in 4 here, you would get a positive as well. OK, so let's try to think now what this would be equal to. So on the interval 1 to 4, what happens with my picture? So 1 is right here. So from 1 to 3, we are negative. So if we have a negative number inside the absolute value, then in order to bring it outside of the absolute value, you're going to have to negate what's in there. So from 1 to 3, I actually have negative v of t dt plus, and then from 3 to 4, the rest of the interval, we're positive. So the definition of the absolute value says I'm just going to get v of t itself when I'm trying to calculate what the absolute value v of t is. So what I'm using here is the following. So that pesky absolute value of x function comes back to haunt you. So it's just x if we're positive or 0, but it's negative x when whatever is in here is negative. So when the velocity was negative, I had to negate it. And when the velocity is positive on this interval, I can just write v of t. So this is from 3 to 4. OK, so then I have the integral from 1 to 3. Negative of the velocity. So negative of this is negative t squared plus t plus 6 dt. And then here I have 3 to 4. And this is just the velocity function I started with, t squared minus t minus 6 dt. So here you have two separate integrals that you're going to need to evaluate and then add up. So I'll do as much as I can with the room I have left. I might leave some of it for you guys to finish, but I'll give you the answer. So integral of this is negative t cubed over 3 plus t squared over 2 plus 6t. Evaluate that from 3 to 1. And then plus, this one over here is going to be t cubed over 3 minus t squared over 2 minus 6t. And this one's evaluated from 4 to 3. So what you're going to do here is you're going to plug in 3. You're going to subtract 1. And then you're going to plug in 4. And from that, you're going to subtract evaluated at 3. So I'm going to do one more line where I plug in everything you'd have to calculate. So if I plug in 3 here, I'm going to get negative 27 over 3 plus 9 over 2 plus 18 minus giant bracket. I'm going to plug in 1 now in all these spots. So I get minus 1/3 plus 1/2 plus 6. So this thing is going to be added to, and then you do the same thing for the second one. So you plug in 4. You get 64 over 3 minus 16 over 2 minus 24 minus giant bracket. I'm going to plug in 3 in all of these spots. And I get 27 over 3 minus 9 over 2 minus 18. Close my giant bracket. Instead of 6 terms this time, there are 12 different terms. But I will save you the trouble again because I'm nice. And this is going to be equal to 61 over 6 meters. So that's the total distance traveled. So look how much more we've accounted for with this one. So over here, just starting from 1 and ending up at 4, just taking those 2 points in time, we just know it went to the left overall, 4.5 meters. But here, taking into account all the twists and turns along the way, this is about, this is more than 10 meters right here. So I hope that process helped out with finding the difference between the displacement and the total distance traveled. So in either case, you're going to look at the velocity, and you're going to integrate velocity. OK, there are another number of examples of the net change theorem that we're going to cover in class as well. But for now, I'll leave it here. So please reach out to me if you have any questions, and give your lecture quiz a try. And I will see you next time.